Welcome, everybody. Today I will share with you some of the new developments and applications of lab-based HAXPES using our PHI Quantes Scanning XPS Microprobe instrument. So for functional material characterization, there is a set of analytical tools that analysts have in access to their study. The type of information that people are looking into is composition, chemical speciation, amount of dopants, morphological properties. More novel materials may require band structure characterization. As you can see, XPS provides a lot of information for functional materials. It is one of the most commonly methods due to mainly its capability not only to provide elemental composition, but also chemical composition. The sampling depth of XPS is 5 to 10 nanometers, which makes it also very advantageous for surface analysis specifically. But at the same time, new materials have interfaces that may be thicker than XPS sampling depths. For electronic materials, for example, there may be a capping layer that is protecting buried active layer. So usually what analysts are doing, they're combining some sort of depth profiling capability with analytical spectroscopic capability to access those deeper interfaces. But we all know that there is no perfect ion gun that will let us spot through material without preferential spotting or inducing potential damage. So hard X-ray XPS providing new opportunities to address some of these limitations of being too surface sensitive of XPS. So what is the hard X-ray? So here we see this spectrum of energies, and we can see that soft X-rays is the one that we usually have at the lab-based system, magnesium, aluminum. These are called hard X-rays. Tender X-rays are often referred to 3 to 5 keVs, and hard X-rays are usually above 5 to 10 keVs. There's actually ISO that is being worked on right now at PNL that will be coming out soon that really defines what is the hard X-ray. But the standard X-ray and hard X-ray has been used interchangeably for the range of energies that we are using in this presentation. So what does high energy of X-ray source gives us? So we all know the basics of photoemission process, that kinetic energy of the electrons depends on the primary energy of X-ray source. So the higher that energy, the higher the kinetic energy of the photoelectron that we will be detecting. And that defines basic parameters such as inelastic mean free path, which defines sampling depths. So here we can see a dependence of inelastic mean free path for several elements, transitions as a function of electron energy. So you can see that the higher the kinetic energy, the higher the inelastic mean free path. If we look at the universal curve that everybody is familiar with, that again describes this inelastic mean free path as a function of kinetic energy, the in-house lab-based systems work between 100 to 1500 EV, and there is a almost linear relationship between kinetic energy and elastic mean free path. This graph is is taken from the paper that was discussing synchrotron-based high energy sources. So HAXPES, let's say at BESI, has a variable energy from 2000 to 10,000 that results in the kinetic energy of the electrons up to 10,000 EV. And that, of course, will result in larger sampling depths. So the benefits, therefore, of using hard X-ray sources, and I would like today to present examples for each of these benefits, is, of course, the obvious, the one that I already listed, is deeper depths of analysis. I will show you that due to deeper depths of analysis, we can really probe interfaces that are thicker than can be accessible by XPS. We can probe below the top protective layer, for example. We can probe non-destructively through some of the heterostructures. And just overall, we can just probe deeper into the bulk of the material. Another very attractive advantage is the reduced effect of surface contamination, and I will show an example of that. and reduced effective ion beam damage at the interface. And I will show you some of the results of that effect as well. Due to having a higher energy of our X-ray source, and of course, now we can have access to higher energy for electron peaks. So now we have additional transitions that are accessible, and they come, of course, with additional chemical information, but also sampling depths that can be varied from one transition to another. As with many dual anode saucers, there is always a desire to shift Auger transitions. So with higher energy X-ray source, we can avoid overlap between core electron lines and Auger peaks. And I will also show example of Auger parameter by combining data from both aluminum and a hard X-ray source. So initially, the hard X-ray photoemission use for photoemission was developed in 70s. So there's first HAXPES that was obtained at the synchrotron using a primary source of 8,000 eV. And it's multiple beam line, of course, picked up, and that became quite a popular technique. So the laboratory sources became available a few years back. The first international workshop for HAXPES was established in 2003, and up to maybe a few years back, most of the presentations were using synchrotron radiation beam lines. But now there is a big shift due to manufacturers now providing lab-based systems with hard X-ray. Now there is a lot of lab-based applications that scientists can share with their colleagues. So there are challenges to synchrotron-based HAXPES, as any other synchrotron-based experiments is, of course, it's quite cost-intensive and difficult to access. It's very highly competitive. If some of you have tried to apply for beam time, you know that the success rate is quite low. And then if you have an access to that, you're successful in completing the proposal and being allocated time, it's usually quite a short time that you're given for the instrument. So you have to be really, you plan your experiment and hope that what you have planned will be successful. Of course, there are developments, but most of the time the systems are not automated for sample manipulation and data acquisition. The sample handling is limited in terms of how many samples you can load at the same time, what sort of shape and size of the sample that you can load in this system. Judge utilization for semiconducting or insulating sample is not available in synchrotron. Quantification is practically impossible because for each energy, especially if you think of variable energy HAXPES, you have to derive new quantification parameters. So most of the studies that you can see that coming out from synchrotron sources is looking at the chemical shift at intensities comparison, but not at the quantitative results. And another disadvantage is that as we increase the energy of the X-ray source, the cross-section decreases dramatically. And that is also true for a lab-based system. So here's we have the relative intensity of carbon 1s peak with respect to aluminum K alpha for different high energy sources. So if we take relative intensity for photon for aluminum equal to 1, we can see that if we use for the same transition silver source, our intensity will decrease 10 times. For chromium source, it will decrease probably 50, 70 times. And for gallium, which is 9,000 EV, and about 9,000 EV energy, it decreases almost 500, 300, 500 times. So intensity drops down, and that requires longer acquisition times. So the optimal range of that allows us to access higher sampling depths, additional transition, at the same time having photoelectron cross sections that provide a significant signal is between 5 and 7 kV. So now there are, like I mentioned, most of the manufacturers have high energy sources. So we can, the silver source is quite easy to implement because it's exactly twice the energy of aluminum source. So Kratos thermospecs, they have their silver source. A few years back, we have introduced a chromium source, and my presentations will be focused on that. And then there is a gallium liquid source that is around 9.25 EV that is available as well. Here's some of the early papers of 64 and 67, 1967, that shows the very early HAXPES using copper K alpha as well, that has energy of 8 kV. So what is the instrument that PHI has that has high energy source? So this is our PHI Quantes instrument that has scanning microprobe sources. So it combines monochromated aluminum K alpha source plus chromium X-ray source. The energy of the chromium X-ray source is around 5400, and it's approximately 3 times larger than energy of aluminum X-ray source, and therefore on average sampling depth is approximately 3 times larger. It is a high throughput, fully automated system that has many capabilities available to scientists. So one of the features that is really unique of our microprobe instrument is the monochromatic scanning microprobe. So here what we see is an image of a grid that was obtained using scanning aluminum K alpha source that has a size approximately 8 micron. So we can generate secondary electron using this microprobe X-ray scanning source to produce SEM-like images. And that is really unique feature because it allows us for 100% certainty in area definition. We have also the capability to use to do depth profiling on this system. We also have optional monatomic and GCIB ion gun. And like I mentioned, this is a high throughput system that has automated sampling introduction, parking positions, and automated charge neutralization. But in addition to that, we also have monochromated chromium K alpha source. So it's also microprobe. The size of the chromium microprobe is 14 microns. So we can also use our scanning chromium source to generate secondary electron images like you see here. And you can see that the 2 sources are exactly at the perfect alignment. So we can do same area analysis by combining 2 different sources. And aluminum will give us its information from more surface sensitive depths, while chromium will give us information from approximately 3 times deeper than aluminum. So this video shows the concept of our scanning microprobe. So we have a scanning electron gun that can define the pattern and the size of which we'd like to analyze. So when we scan electron gun on the surface of our anode, the same pattern will be produced on the surface of the sample. And then we have a shutter, and we can do exactly the same using chromium source. So we can define the air spot of our both aluminum and chromium X-ray source, as well as the pattern. We can run a raster over large areas to average, for example, signal, or specifically focus on multiple small areas within the sample. So now let's look at some of the examples of the benefits. So I'm going to show you a few of the applications that we can obtain using a combination of aluminum and X-ray source. So of course, like what I mentioned before, is the greater depths of analysis. So here's an example that we usually have a sample that is 25 silicon film. And when you look at this film using aluminum X-ray source, of course, you don't only detect silicon oxide. While using chromium source, you are detecting both metal peak and oxide peak. So we are probing beneath these 25 nanometers sampling depths. And you can see that in elastic mean free path for the same transition here as a function of kinetic energy. So it's 3 times larger for using chromium source. That results in 3 times larger sampling depths. This is an example of using the microprobe capability. So here we have from exactly the same part of the solder ball that we can navigate to using just optical camera, but then we can use both chromium X-ray source and aluminum X-ray source for navigation. So we can induce these secondary electron images and obtain these images that as we call SXI, and then we can select areas for analysis. So for example, in here, we can select an area on the ball and it obtains small area spectra using aluminum source and chromium source. And of course, the area that you can, or the X-ray beam size can be adjusted based on the areas of the features that you would like to analyze. So when we do that, we can see that for this is a tin, a solder ball. So we can see that using chromium source in tin 3D transition, we detect significant peak from metal. While using aluminum source, we mainly detect oxide with quite small amount of metal present. So this is also quite a unique feature of being able to do HAXPES using small area analysis. On synchrotron is usually larger area of analysis or not as flexible to change your spot size. And something that you can do within the same secondary electron image is you can select multiple points. Here we have just two, but you can select many more points within this secondary electron image and obtain a spectra using our small microprobe source. So with aluminum, we would be looking at silicon to P transition, but now with chromium source, we can actually now have access to 1s transition, which we can also analyze on the ball where we don't expect to have any silicon present, and off on the background where you have really obvious presence of silicon. So now let's look at the reduced effect of surface contamination. So of course, it depends on how dirty your samples are, but adventitious contamination layer usually between 1 to 2 nanometers. So if you think of how much carbon contributes to the overall sampling depth, of course, it depends on the transition, but probably 20% of the signal will come from that contamination layer. And that contamination layer, of course, attenuates the signal from beneath it. While for chromium, we are analyzing 3 times deeper overall signal. So now this 1 to 2 nanometer becomes a much smaller fraction. And this is just an example on the stainless steel sample. You can see that we still detect carbon, but it is really much smaller intensity, and its attenuation is much less significant than using aluminum source. So you don't need to do any sort of cleaning to see beneath that contamination. But it really becomes significant for materials where carbon is a part of your design. So it can be, you can think of this let's say, carbon nanotubes, graphene type materials. So here's an example of max phase. So this is a bimetallic phase based on carbides. And using our microprobe, we can find individual flake. And then within this XI image, we can define an area for analysis. So in this case, we're using the smallest microprobe. So around 8 microns for aluminum, around 14 microns for chromium. And we can obtain small area spectra. So you can see that using aluminum source, we have a huge peak from adventitious carbon, and I normalize it to carbide peak. And while with chromium source, we still detect a little bit of carbon, but it's much less prominent. So we don't need to do any cleaning using ion gun if we are concerned that we may induce damage, for example. And here's an example of aluminum to S transition where we see only oxide at the surface. So if you have oxidation, you will see that present in the aluminum X-ray source. While in chromium X-ray data, we can see both oxide and carbide present. And in titanium 2P, you can see that you have quite big oxide peak present in aluminum X-ray data, while it's mainly carbide that is present in the deeper layers. So you can probe beneath that contamination layer to really confirm if you have expected stoichiometry, which becomes really important for carbon-based materials. So now let's look at the buried interfaces analysis when we are using argon sputtering. Of course, when we are looking at beneath the sampling depths of chromium source, we need to do depth profiling for many structures. So when you look at using monatomic argon, you remove the partial layer, and sometimes, of course, it's very material dependent. You can induce some damage. And there are some models that have been applied to see what is the thickness of the damage. But so this is just a cartoon that shows that, for example, for titanium nitride, when you will sputter using 1 kV monatomic argon, your damage zone will be equivalent to your sampling depths using XPS. So you will definitely detect signal from the damage zone. While for HAXPES, we are detecting much thicker. So we are still capturing a little bit of signal from top, of course, but it's an integral signal. So we are detecting beneath the zone of the potential damage. And here's an example of 3 spectra selected at 3 different points during the depth profile. And in aluminum source, this is, as soon as you start picking up this buried tin layer, immediately you start seeing reduction. While in using chromium source from the same sputter cycle, you can see that you start picking up a little bit of reduction, but much later in time. So you can think of using chromium X-ray source to give you virtually damage-free depth profiles. So what are the sampling depths that we're looking into when we're really trying to develop this experiment? So if you look, again, it's based on the settings of the ion beam that you're using, but on average, the ion beam damage is approximately 15 nanometers or more. So you can see that with aluminum transition for some most common type of materials that we would do for semiconductor industry, electronics, where we'd use depth profiling, we see that our sampling depth is really small. It's less than 10 nanometers. So we will analyze this potentially damaged area. Silver source extends it a little bit, but it's really on the borderline. While with chromium source, you really start accessing much deeper layers, and you are able to probe beneath that ion damage zone. So now let's look at what gives us access to higher core electron energy, so different photoelectron peaks. So this cartoon shows how many more transitions we now have thanks to chromium source in comparison to aluminum. So the shaded areas of the aluminum, these all dashed ones, that are not accessible. But the chromium, we have access to many more of 1s, 2p transitions that can provide us additional chemical information, chemical shift information. So this is just looking at the silver source comparison of a survey acquired from silver foil using aluminum and source and a chromium source. So that you can see that you're extending, of course, the range up to 5400 EV, and you're detecting additional 2s to p transition. And something that you immediately see, you're shifting your Auger transitions, and that comes as advantage of using higher energy X-ray source. You can think of, if you have multiple transitions now, you can think of creating a depth profile, chemical depth profile information without any tilting or without any sputtering. So here's an example of using 2 different transitions for titanium material. Titanium 1s has a really high binding energy, so almost 5,000. So it has really low kinetic energy, and it comes from really shallow surface sensitive depths of approximately 3.5 nanometers. While titanium 2p has really high kinetic energy. So we're now sampling up to 24 nanometers. So you can think, you can plan those experiments, and you can look at the chemistry of your transitions at the surface versus deeper layers, and that can tell you a lot about whether there is oxidation happening, gradients, segregation, without any sputtering or tilting. So it's really advantageous to having those extra transitions. Another advantage comes from the fact what I mentioned before, that we are losing intensity using higher energy sources. So if you look at the photon energy as a ionization cross-section, and if we'll focus, for example, on silicon to P transition, we have intensity or cross-section, which is proportional directly to intensity of using aluminum source. We are losing several orders of magnitudes using chromium source for silicon to P. So if you would like to analyze silicon to P, you would have to spend more time acquiring the data. But now we have also access to silicon 1s, and you can see that for silicon 1s transition, we have equivalent cross-section, so comparable to ones that are that we know for aluminum X-ray source, so we can expect equivalent data acquisition times for those transitions. So shifting Auger transition is something that comes with a great advantage, and I have a few examples throughout this presentation. So you already have seen one for silver. One of the most challenging types of analysis using aluminum X-ray source is transition metals. In catalysis, electrocatalysis, there are a lot of materials that are based on bimetallics or trimetallics using cobalt, magnesium, iron, nickel, and where all of the main peaks are present, there is a huge overlap between Auger features and main peaks. So this is just the reference data from manganese and from nickel using aluminum source. And you can see that it's overlapped, and it's really hard to use these transitions for quantification. While using chromium source, we're shifting all of this transition to the higher binding energy, because the kinetic energy of Auger transition is fixed. And now we have really nice, pure of overlap transition that we can use for accurate quantification and chemistry identification as well. The Auger parameter is something that was invented a long time ago, and it's really useful for chemical analysis. And it actually has been reinvented, so to speak, or revived with development of high energy sources. There was really interesting work that was published from our customer at EMPA, where they created really interesting experiment. They wanted to look at different alumina compounds. But of course, with when you are using combination of your main transition and Auger transitions for deriving your Auger parameters, the signal comes from different sampling depths. So if you really would like to look at exactly the same sampling depths where you have the same contribution of your oxides, let's say a mixed oxide phases, you would like to be at the same sampling depths. So by using the tilting capability of our stage, we can do analysis at different angles, and using two X-ray sources, you can find that match of putting and probing at a constant probing depths your Auger transitions and main transitions using chromium and aluminum sources. And you can see that we can derive these Auger parameters for amorphous alumina and alpha alumina at exactly the same sampling depth. So very elegant experiment where it's there's no concerns of whether you're probing different contributions from oxides on top versus deeper in the bulk. So quantification of HAXPES data is something that I mentioned as a challenge overall. Of course, all of the manufacturers that provide now the lab-based systems, the data do come with quantification parameters, and usually they are based on the Wagner cross sections, so they are theoretical or empirically derived cross sections. We have started a project several years ago to derive experimental RSFs. So we are working with IMEC, Leti, and NIMS to experimentally measure relative sensitivity factors using chromium key alpha source. So we've started with references that we're analyzing. So we are looking at ionic liquid that are perfect, have perfect stoichiometry, so really easy to work with, stable under X-ray gun, and don't require any charge neutralization. And also we're looking at some other compounds containing silver, because silver is our reference material when we acquire the data, but we need to know what is the RSF for silver. So we have looked at triflate of silver, where we do assign fluorine RSF equal to 1, and then we can derive RSF for silver transitions. So this is where we are. We have released a second database, experimental database to our customers a few months ago. So that now there are 53 elements that have RSFs for all transitions that have been analyzed in collaboration with IMEC and CEA. That is really an important and ongoing project. So of course, we would like to complete whole periodic table, so we have equivalent database to what we have for aluminum X-ray source. Along with that quantification, we are also doing chemical shift database. So you can see that the chemical shift, of course, it's known for transitions such as silicon to P and silicon to S, but now we have new transitions. And silicon 1s, we see that that silicon 1s actually has higher chemical shift when silicon is bounded to nitride and oxide than the other two transition, and it doesn't have any spin orbit splitting, so it really helps with chemical identification and resolving your chemistries that may be mixed. And then there is another example for aluminum. So we have again aluminum 1s that is now accessible, and we are providing the shift, and you can see that it's 2 eV for nitride and 1.6 eV for oxide. So we are putting together that, and there has been a special issue that of surface science that I will show on the next page, on the next slide. But of course, when we derive experimental RSFs, we need to know how good is our quantification. So here's an example of quantification for 3 different silica-based compounds, and you can see the average error from expected stoichiometry is less than 5%. There's an example of quantification for alumina and nitride. When you have multiple transition, then you can combine, for example, for moly-selenide, you can combine 2 S transitions from both molybdenum and selenide to P, 3P, and we are providing all of these RSFs for all transitions that we acquired, and you can see the quite accurate quantification. And here's an example of silicon germanium bimetallic compound. Also, we can combine different transitions from both silicon and germanium to extract quite good quantification results. So it's really important feedback that we are getting from compounds where we know what a stoichiometry is. And this special issue of Surface Science Spectra that was published last year, it's higher energy XPS special issue. Our collaborators, IMEC and CEA, and our customers, BAM, they have published now papers from quite large collection of compounds. So the chemical shift is available for anybody who may be using our system for chemical analysis. So it's really important project that is ongoing. We all know the advantages of angle-dependent XPS, but we can do exactly the same using chromium source. We can do a variable angle or angle-resolved experiment by changing the escape electron depths by tilting the sample. So it's a non-destructive way to probe thicknesses of multiple layers or single layer structures. So we have, a few years ago, we have introduced a new package that is called StrataPHI that allows calculations of thicknesses for thin film structures. And the assumption of this model is discrete layers. And really a unique feature of this software that if you have non-repeated layers, if you have unique chemistry in each layer, you don't need to do angle result dependent analysis. You can actually extract structure from a single takeoff angle spectral data. And this is a great metrological tool because you can imagine that you can increase your throughput of data acquisition. And therefore we have incorporated many data processing automations in this package as well. So it's algorithm that is based on the straight line approximation. So we are basically, I'm not going to go into equations, but what we're modeling is intensity as a function of takeoff angle. We know that, so we can calculate the Z, what is the thickness of each of the layer within our structure. And here's an example of using HAXPES. So here's an example of you having 3-layered structure. So we have TEM that probed at multiple positions within the TEM. We know that it's approximately 1 nanometer alumina on top of 2.5 hafnia on top of 1 nanometer of silicon, and substrate is silicon. So now we have access to 1s transitions. That's first advantage, and we don't have to deal with doublets. It's easier to process. And these transitions that we can also have access to hafnium 3D transition. And you can see that this table shows an inelastic mean-free path within each layer for each transition. So you can see they're quite similar. And for each layer in the model, it actually takes into account the properties of the layer. So we really take into account the transport properties while electrons traveling through the layers and being detected to create this sample structure. And you can see that it's quite accurate. We got quite accurate result, and certainty that is being also derived as a part of the model from this StrataPHI using angle-dependent HAXPES analysis. Some applications that we are working together with our customers at LEDI, and there's a published infrared discussion paper, lots of really interesting examples. So this is for gallium nitride-based devices. Gallium nitride is, of course, very challenging to analyze using aluminum K-alpha source. You cannot quantify nitrogen due to overlap with gallium Auger transition. Chromium K-alpha shifts gallium Auger transition. There is no overlap, so we can really accurately quantify nitrogen. And now we can potentially detect much deeper gate oxides. So here's the typical, the gate oxide thickness is 30 nanometers. And we wanted to see whether we'll be able to detect this. So we started with model systems to develop the methodology. So we have looked at different alumina thicknesses on top of gallium nitride. So we have 5 nanometers, 10 nanometers, 20 and 30 nanometers thick alumina on top of gallium nitride. And you can see that if I would normalize, there's actually a peak that we can also, that we detect use for 30 nanometer alumina layer as well. And using our StrataPHI algorithm, we can obtain the structure and pretty, the nominal thickness and pretty accurate thickness that we can obtain using HAXPES data for these type of materials. And of course, the chemistry is really important. So we can look at the reference materials, and we can see that we run these references using a chromium source. For bulk reference materials, we know that shift between gallium oxide and gallium nitride for gallium 2p transitions. And then now when we look at the actual HEMT device, we can see that we detect a little bit of oxide. We detect the expected peak of gallium nitride. And it seems to be that we may have a little bit of a layer by the metallic or reduced form of gallium at the interface with aluminum detected as well. Very exciting capabilities are now available also for electrochemical devices. So we have capability in situ to heat and cool, but we can provide solutions to move from, let's say, a glove box to the analysis without exposure to the air. So transfer solutions for that. And this is an example of 4-contact sample stage. So we can do polarization studies. And this is opens capability to do Operando, a lab scale HAXPES. So again, with collaboration with CIA, they have created a cell and they put it on the sample holder that I showed before, where you have capability to bias. And with our microprobe, X-ray source, we can actually obtain an SXI image, the secondary electron image of this cross-section. And so we can really focus on selecting which areas to analyze. And there's more details that are published in this paper, but it shows you that we can basically establish this experimental protocol by biasing the stage to the positive and negative. We can move our platinum reference spectrum for Operando studies. And I invite you to look at this paper to study, to learn more about these electrodes that have been developed and studied by our customers. So this slide kind of brings me to the end. I think I showed you the advantages and we discussed several examples of these advantages of using hard X-ray sources.